Hi everyone, it's Albert. Today let's solve the median question from the weekly contest, find the most competitive subsequence. The question statement, so we are given an integer array nums and a positive integer k, and we have to find the most competitive subsequence of nums of size k. In arrays of subsequence, it is the resulting sequence obtained by erasing some elements from the array. So basically, it is some elements from the array. They don't have to be contiguous, but the order has to be maintained. And here we define a subsequence A is more competitive than subsequence B if in the first position where A and B differs, subsequence A has a number less than the corresponding number in B. For example, an array 134 is more competitive than array 135 because the first position they differ is the final number, and 4 is less than 5. So for example 1, among the every possible subsequence, the subsequence 26 is the most competitive one. And for example 2, for the subsequence of size of 4, the subsequence 2, 3, 3, 4 is the most competitive one. In a data constraint, the length of the array can go up to 10 to the power of 5. And the intuition to solve this question, the main idea is to find the smallest elements so far and increasing elements afterwards, but with some key conditions, which we will discuss later. And this is a perfect application of data structure monotonic increasing stack. So now let's look at the code. Okay, the code is pretty concise. First, create an empty stack and then go through the array. And the key here is to maintain monotonic increasing stack. So here we will specify the condition when should we pop elements from the stack. So when the stack is not empty and the current element is smaller than the last element in the stack. And here is the key condition. So this condition is saying that if we pop one element from the stack, and if we have enough elements in the remaining arrays, if the total is bigger or equal to k, then we are safe to keep popping elements from the stack. And if the current size of the stack is more than k, and the elements in the nums array are increasing, then we can just append the current element, nums I, into stack. And finally, we can just return stack as the final output. Now let's see the code in action. Okay, and here we'll be looking at a custom test case. This is a special test case because the smallest element in the nums array is 2, which is the final number. But the actual output, the most competitive subsequence, is array 8, 80, and 2. And here we will see how the code works for this case. Okay, and starting from the first element, since currently the stack is empty, so we will just push 71 into stack. And the next element, 18, since 18 is smaller than 71, so we will pop 71 from the stack and push 18 into it. And next element, 52. 52 is bigger than 18, so we will just push 52 at the end of the stack. And then the same, 66. So now we have 3 elements in the stack. And the next element is 8. And here we can see that since 8 is smaller than the all 3 elements in the stack. And the main reason why we can pop all 3 elements from stack is because we still have 2 remaining numbers in the nums array. So we are still able to make a stack with size of k, which is 3, later on. So this is what the key condition is checking. And the next number is 80. We will just push it into a stack. And the last element is 2. And even though 2 is smaller than 80, we don't have enough remaining numbers to push into stack. So no elements from stack will be popped. And we will add 2 into stack. So the final result is a subsequence 8, 80, and 2. And this will conclude the algorithm. Finally, let's do a quick review. So the main idea to solve this question is to find the smallest element so far when we are going through the nums array and increasing elements afterwards. And the data structure to be used is a monotonic increasing stack. But notice that the key condition is we only are able to pop stack only if we have enough elements in the remaining array. And the time complexity of this approach is linear time. And the space complexity is big O of k, where k is the size of the stack. And that will be all for today. Thanks for watching. If you like this video, please give it a like and subscribe to my channel, and I will see you in the next one.